Okay, now to look for horizontal asymptotes if they exist. Now I've got three forms of the function here. I can use any of them that I like. You might want to go with this one because you think it's a giant fraction, but what you'll find is that if you throw that method that we've learned of dividing everything in this giant fraction by the highest power of x on the bottom, which is x, when you divide all these three terms by x, what you end up with is actually this form. So if you went ahead and did that, that would be fine, but you'd sort of realise, oh, I've maybe wasted a little bit of time there. So instead, when you're looking for horizontal intercepts, the main thing you want is for x's to either be really nice and simple, so that when you say as x approaches infinity, they'll be something nice and simple, or you want them on the bottoms of fractions, so that you can say as x approaches infinity, this fraction would approach 0. Now this form of the function is fine for this. I can say as x approaches infinity, y is going to approach, and then just think it through. Well, that's going to be infinity, and this part's going to be as good as 0, so y is going to approach infinity. What does that mean? It means that there aren't any horizontal asymptotes, because as x gets really, really big, y can get really, really big too. It can be whatever it likes. So it's moving up to a large number. So there isn't a line that y can't be. So therefore, no horizontal asymptotes. Okay, now we're getting down to thinking about the shape of the curve and the derivatives. So we haven't differentiated the curve yet. That would be a good thing to do next. I'm going to just rub out some of this so that I've got more space. In fact, I'll rub out all of that because you've probably written it down already. Okay, so this is the form that I like for differentiating. That's going to be nice and easy. So our first differentiation of it, we'll get 1 for this term. And here, if I bring my minus 1 down the front, I'll get minus 1 and then x to the minus 2. So minus x to the minus 2. And if I want to, I could write that like this. It's handy to put it in another form because that might just make it a little bit more user-friendly when I come to let it equal 0. Okay, now I can easily differentiate this again and get f double dash x. That part becomes nothing. And this part, the minus 2 comes down and joins the minus 1 that's already there. That makes 2. And then the x gets raised to the power of minus 3. So I've got it that way, or I could write it like this if I like. All right, now what are we going to do with our derivatives again? Well, this helps us look for stationary points, and this one helps us decide what types of stationary points they might be, and it also helps us look for points of inflection. So let's let the first derivative equal 0 and see if we've got any turning points. So that means y minus this, 1 minus this equals 0. And then adding this part to both sides, I get that. And multiplying both sides by x squared must be 1. And that means that x must be plus or minus 1. So that means there's 2 stationary points on this graph, 2 potential turning points or horizontal points of inflection. We're not sure which yet. Now we're not sure where they are in space. So let's consider when x is 1 and when x is minus 1, let's find y. Now because we've got f of x terminology here, I don't need to write when x is 1, y is something. I can just say what's f of 1. And sub it into any of these 3, whichever one I like. 1 plus 1 is 2. That's simple. And minus 1 is minus 2. So that means I've got a stationary point, and I can just go straight ahead and plot it at 1, 2, and minus 1, minus 2. So 1, 2, let's label that. And minus 1, minus 2. Now, not only is it a dot that I can make it like a just mini little flat spot there, just a tiny, tiny flat spot to remind me that it is a turning point, potentially, or some sort of stationary point. We're not sure yet, we need to investigate. Now, we've got 2 ways to investigate. We could look at the gradient either side, but I'd have to sub in a fraction here, like half or something like that. That seems a little bit hard. I've got the second derivative just sitting there, so I may as well use it. So the next thing to do, let's use this little bit of, let's use this bit of board in here because I think it can just be skinny. Obviously I'd work down on my page and there's quite a lot of working I've done here just to graph one thing. I can say f double dash x, no not x, I want 1, don't I? And subbing 1 into this, I've got 2 over 1, it's 2. Now what does that mean? Well, if the second derivative is positive, it means that it is a minimum turning point. It's got concave up and like a smiley face. So that's our point over here. We can draw a little mini smiley face there, and we know it does that. Whereas when f double dash x is, when we're sub minus 1 into f double dash x, we're going to get on the bottom here minus 1, and 2 over minus 1 is minus 2. Now that's negative, which tells me that it's concave down there. So that means that this turning point is a little frowny face section. All right, the other way that we can use our second derivative, we said we wanted to check for any points of inflection. So just think through, let f double dash x equal 0, and think, can it equal 0? Well, 2 over x cubed, can that equal 0? No, because if you've got something divided by something, you can only get 0 if the numerator is 0, and the numerator here is 2. So there's no values of x that are going to make this true. Therefore, there's no points of inflection, and you can write POI there for short. All right, now we're pretty much ready to graph it. So we can see what's going to happen here. We've got an asymptotes. The graph must approach that and head upwards, getting closer and closer, and coming down here it must get closer and closer too. Now you could be at the point where you're going to say, well, I've used my whole curve sketching menu and I'm still not quite sure what happens over here. Well, look for your clues. We know that every time, we know we've got an odd function, so whatever happens up here happens down there too.